Titanium sounds like something straight out of a sci-fi movie. It's light, incredibly strong, resistant to corrosion, and used in everything from aircraft to medical implants. But here's the surprising part. Despite being one of the most abundant elements in Earth's crust, pure titanium is actually very difficult to produce. So how do we turn dull, ordinary minerals into one of the most advanced metals on the planet? Today we're breaking down exactly how titanium is made, from raw ore all the way to the finished metal, right here on History of Simple Things. Titanium was first discovered in 1791 by a British clergyman and mineralogist named William Gregor, who found an unknown metal while studying black sand in Cornwall. A few years later, in 1795, German chemist Martin Heinrich Klaproth independently identified the same element and gave it the name titanium, inspired by the powerful Titans of Greek mythology. Even with its discovery, however, titanium stayed mostly a scientific curiosity for more than a century because it was extremely difficult to isolate in pure form. It wasn't until the 20th century that scientists began making usable quantities of titanium, and the real breakthrough came in the 1940s when William Justin Kroll developed the Kroll process. This method finally made large-scale titanium production possible, opening the door for its use in aerospace, military technology, and later in medicine and consumer products. From that point on, titanium transformed from a rare laboratory metal into one of the most important engineering materials in the modern world. Titanium doesn't exist in its pure metallic form in nature. Instead, it's found locked inside minerals, the most important of which are rutile and ilmenite. These minerals are mined from the earth, often from sandy deposits or hard rock formations. Ilmenite is more common and cheaper, but it contains iron along with titanium, which makes it more complicated to process. Rutile, on the other hand, is richer in titanium dioxide and is easier to refine, though it's less abundant. Once mined, these ores are crushed and concentrated to increase the amount of titanium-containing material. At this stage, what we have is still far from metal. It's essentially refined dirt with a high titanium content. Now comes the most important step, turning it into actual titanium metal. This is done using the Kroll process, and it actually begins with a crucial chemical transformation. First, titanium ore, usually ilmenite or rutile, is heated to very high temperatures and reacted with chlorine gas and carbon. This step, called chlorination, converts the titanium in the ore into titanium tetrachloride, a purified liquid compound. At the same time, unwanted impurities like iron are separated out through distillation, leaving behind a much cleaner titanium source. Once purified, the titanium tetrachloride moves directly into the next stage of the same process. It is placed in a sealed, oxygen-free reactor and heated with molten magnesium. The magnesium strips away the chlorine, producing pure titanium metal and magnesium chloride as a byproduct. What remains is not a solid block, but a porous material called titanium sponge. This sponge is extremely pure but still needs to be melted in controlled conditions to become usable metal. Once the titanium sponge is produced, it's crushed, cleaned, and melted to form solid metal. This is usually done in a vacuum or inert atmosphere to prevent contamination. The sponge is placed into a furnace and melted using techniques like vacuum arc remelting. This ensures the titanium remains pure and uniform. The molten metal is then cast into ingots, large blocks of titanium that can be further processed. These ingots are the starting point for making usable products. They can be rolled into sheets, forged into parts, or drawn into wires depending on the application. If titanium is so abundant, why is it expensive? The answer lies in how complicated and energy-intensive the process is. Unlike metals like iron or aluminum, titanium can't simply be melted out of its ore. It requires multiple chemical reactions, high temperatures, and controlled environments to prevent contamination. Each step adds cost, time, and complexity. The Kroll process itself is not very efficient, and despite decades of research, there's still no widely adopted, cheaper alternative. That's why titanium is often reserved for high-performance uses where its unique properties justify the cost. Because of its strength-to-weight ratio and resistance to corrosion, titanium is used in some of the most demanding environments. In aerospace, it's used for aircraft frames, jet engines, and spacecraft components. It's strong like steel but much lighter, which helps improve fuel efficiency. In medicine, titanium is used for implants like joint replacements and dental screws because it's biocompatible. It doesn't react negatively with the human body. You'll also find titanium in high-end sports equipment, marine applications, and even some consumer products like watches and smartphones. Wherever durability and weight matter, titanium is often the material of choice. What makes titanium fascinating isn't just its strength or its lightness, it's the journey it takes to get there. Starting as a common mineral in the ground, it goes through extreme heat, complex chemistry, and careful refinement before becoming a high-performance metal. It's one of those materials that reminds us how much effort goes into the things we often take for granted. The next time you hear about titanium in a plane, a medical implant, or even a gadget, you'll know there's a long and surprisingly complicated story behind it, and that's exactly what makes it so interesting. Thank you for watching. If you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you an acknowledgement for your contribution. Thank you for joining us on this journey through the history of simple things. Don't forget to like, subscribe, and stay tuned for more stories woven through the smallest details.